Hi there, this is the first of a series of videos that uses the Powermon to measure or investigate something. In this case, the Energy8 Plus charger from Ansmann. I have had this charger for quite some time and I was never all that happy with it. When it works, it does a good job, but boy is it finicky about whether it likes the battery or not. I often found it rejects batteries that other less sophisticated chargers accept and charge with no complaints. So I thought finding out what the Ansmann charger does when it charges some batteries and rejects others would be a good test case to use my newly built and calibrated Powermon in earnest. If you're not familiar with Powermon, there are a few videos about it when I was designing and building it, and you can download the software and schematics on my Github page. Links are in the description below. Without going into lots of details, I want to also briefly mention a couple of software changes in the Powermon that are the result of using it for these investigations. This is the basic setup I plan to use. Basically, the Powermon sits in between the battery to be charged and the charger. Although I originally planned the relay on the Powermon to disconnect at the end of a run, for example when a minimum voltage has been reached or a maximum time expired, I found out that it works just as well to manually start a run when everything is ready. For this mode, the relay is initially off until everything is wired up. Then the relay is manually activated. You could still make it turn off automatically, for example after so many hours or after, say, 3000 milliamp hours of charge or whatever, but I normally don't bother and instead let the charger go into trickle charge until I happen to check the status. Don't forget, these runs take many hours and I often let it run overnight. I rearranged the button assignment in the run menu mainly to add the new start function because it greatly simplifies running these tests. The start function does three things in sequence. First, it resets all the statistics such as runtime, capacity, peak values and so on, which is the same as pressing the already existing clear function. Then it starts recording and as the last step it activates the relay. You could do all these actions individually already, but with the start function it's just one press. It also means all recordings start at 0 and the recording also captures the very first interaction between the battery and the charger when the relay activates and connects the battery to the charger. The second change was that a snapshot turned out to be so useful that it's now a separate function from recording and has its own snapshot file. Every time snapshot is pressed, one line is added to the snapshot file. If it doesn't exist, it's of course created. The data stored is a lot more than what was available in recordings and contains basically everything that you can select for display in the various fields, including peak, average and low voltage, currents and so on. The timestamp shows date and time when the snapshot was made. So for example, this one was done on the 8th of March 2019 at 21:17 and 20 seconds. Although the format is comma-separated values, I named it a .txt file. Because it contains data from potentially many different runs, it's probably not making too much sense to import it into a spreadsheet. But you could do it if you needed it. The sample here is cut off at the right because the screen is not wide enough to display all the fields. The last change in Powermon concerns the recording in the rec change mode, which is what I'm using most often. Rec change basically only adds a line to the recording file if either the voltage has changed by at least 10 millivolts or the current has changed by at least 1 milliamp since the previous line was recorded. The advantage of this method is that fast changing values are not missed and always recorded at maximum resolution, but during phases where the values are basically constant, nothing is recorded. This can significantly reduce the recording file size, especially if charging or discharging batteries over many hours. Very early in my investigations of the Ansmann charger, I noticed that plots of the data were full of these long sloping lines, which did not make much sense. On closer inspection of the data, you see here that at second 5557.2, the voltage was still 1.4333 volts and the current 400 milliamps. The next entry is almost 6 seconds later. At 55631, the voltage is still 1.433, but the current has dropped to about 5 milliamps. The plot software connects these two current measurements, and so we get a slope showing an apparently gradual drop from 400 milliamps to 5 milliamps over 6 seconds. This is obviously not right, because we know that right to the sample, a few milliseconds before 55631, the current must have been still 400 milliamps, because if it were different by more than 1 milliamp, the sample would have been included in the recording file. I considered what could be done, and the proper solution is that if a new line is recorded because of a detected change, then the sample immediately before that is also recorded. In other words, I always record the first and the last sample of the period where the values were unchanged and skipped. While it might seem wasteful to essentially record two identical lines following each other, they aren't really identical because their timestamps are different, and that's crucial what the plot needs to draw the graph correctly. The graph on the right here shows the effect. This is of course from a different recording, and the data has nothing to do with the sample on the left. But you can see that at 7.6 seconds, a voltage of 1.1337 and a current of more or less 0 was recorded. About 18 seconds later, at 26.2, the current jumps to 1.459, which causes an entry in the recording file. But the last sample before that, 26.1, is also recorded. And it has the values that differ so little from the 7.6 volts that they are considered the same. The effect is that instead of a long 18-second slope upwards from 0 to 0.149 milliamps, we now see a horizontal line followed by a spike, which is the correct behavior. Another way to look at this is the idealist graph on top here, showing the same samples as stars for both the old and the new function. The samples that are recorded are shown in black, while the identical samples that are skipped are shown in gray. You can clearly see how the old method of recording only data that has changed skews the data to be plotted, while the new method shows the correct behavior. With all that out of the way, let's examine the Energy8. It has those four big bays. The outer ones can take two AAA or AA batteries each, or one C cell or one D battery, while the two middle ones can only take one AAA or AA each, but can also take a C or D battery. So we have a maximum of 6 AAA or AA that can be charged simultaneously, and then there's of course two slots for 9-volt batteries, so a maximum of 8 batteries, hence the name Energy8. The bottom is secured with 8 security screws, but they are no obstacle for a spanner or pig nose bit. And with a little persuasion, the bottom plate comes off. 5 screws secure the PCB to the rest of the chassis. It lifts off, but not very far, because the 6 white wires that connect to the sliders in the battery slots. I would have to desolder them to take the board out completely, but I decided not to go that far. The springs you see here go into the matching holes and connect the PCB to the terminals in the 9-volt battery slots. You can see how the white wires connect to the sliders. I try moving one to demonstrate. There's hardly anything on the other side of the PCB, at least in this area. you can make out 4 temperature sensors that still have a little heat sink compound on them that plug into holes on the battery compartment. I suspect they sense the heat through the plastic. It appears that the charger senses the battery size depending on the height of the positive pole of the battery. There are contacts for each battery size. It is not determined by the position of the slider as with some other chargers. The microcontroller is a Sino-Wealth SH69P55A, which is a 4-bit microcontroller and a rather strange choice for this particular design. The SH69P55A is a controller that is designed for microwave ovens and washing machines, and full of features that seem completely wasted in the Energy8 charger. The controller has a full-blown built-in LCD driver and a built-in LED driver, but the Energy8 has neither. In fact, it has no display whatsoever. The chip includes an automatic keypad scanner. Where is it? There it is. But the Energy8 has neither buttons or keypads. And it features a 2-channel tone generator, but there's no speaker in this charger. It can also detect AC zero crossing to smoothly switch high-power AC components like washing machine motors or microwave transformers on or off, but the charger has obviously no need for any of this. Okay, it also has plenty of I/O pins and a 10-channel 10-bit ADC, so I have no doubt that it can be pressed into the job of managing a charge, but with no display, keypad or speaker, it just seems a very odd choice. The other prominent device on the PCB are 8 D882 NPN transistors that can handle a maximum of 3 amps collector current. These are presumably controlling the charge current to the batteries. After putting the charger back together, it is clear that measuring the charging of batteries with Powermon must connect the correct pad on the plus side on the charger. The lowest for AAA and the one immediately above is for AA. In the end, I decided to make a wooden dummy AA with a screw as a contact for the plus side. Since the body was a little undersized, I used yellow electrician tape to bulk it up until it had the same diameter as a AA. This method, of course, means that the temperature sensors won't be measuring any heat generated by the battery, and we need to keep that in mind and, if necessary, terminate the charge manually if a cell gets too hot. As the first test of this setup, I'm going to charge a fully discharged Energizer 1850 mAh AA cell. On the Energy8, the red LED comes on, indicating an empty cell, and quickly changes to blinking red-green, meaning refreshing. On the Powermon, we can see that this means discharging the battery with about 300 milliamps with occasionally very short spikes of positive charge. After slightly more than 1 minute, this changes to green blinking, which means pre-charging. We can see this consists of large pulses of quite high current, so much that the Powermon automatically auto-ranges from A to B, which is this 800 milliamp range. Sometime later, I noticed that the green blinking pre-charging had changed to solid red, which means charging. This seems to be mainly a more or less constant current of about 620 milliamp. 4 hours into the charge, I looked at the Energy8 and noticed that the solid red light had changed to solid green, which means ready or fully charged. As there were still pulses of 500 milliamps or so every so often, and because the accumulated charge was 1946 milliamp hours, which I felt was a bit short for a 1850 milliamp battery, given there are some losses, I decided to let it run a bit longer and see what would happen. After a total of more than 6.5 hours, the charge had slightly increased to 2057 milliamp hours. Time to look at the recording. I wrote a little utility using Python and matplotlib, which allows me to graph the voltage in blue and current in red over time. You could also use the graphic function of a spreadsheet program for that, but this utility is way faster, interactive, and it can handle much longer recording files. Well, at first glance this looks a little bit strange, but that is because the red dense current plot hides the blue voltage plot underneath. Let's zoom in at the beginning of the charge. Here we have the red-green blinking refreshing stage. We see that the charge current or discharge current is about -300 milliamps with short spikes of about 800 milliamps every second. Interestingly, they're not always there, but the voltage is still spiking. The current spikes are exactly one sample wide, so I think this is a problem of the sampling frequency of Powermon. We might have just missed the current spikes until the timing drifts a bit more and we catch them again. Similar, we may sample on the rising or falling slope of voltage spikes, and therefore the voltage seems to go up or down. Moving and positioning the graph on the camera takes a lot of time, so for the rest of the video I'm going to use stills instead. Here is the green blinking pre-charge phase. We can see nice fat current pulses of 50% duty cycle with about 2 seconds pulse width. The peak current is 800 milliamps, dropping to around 700 milliamps. There seems to be a pattern of 2 pulses followed by a slightly longer pause of 4 seconds. I'm slightly suspicious about that peak at the beginning of each pulse because it initiates a current range change in Powermon. This overshoot is quite pronounced, for example here in the ready phase, during these pulses of 2 seconds length with 800 milliamps peak and 500 milliamps sustained charge pulses, which is the Energy8's way of trickle charging. Just to check if there would be a difference, I switched Powermon to manual range, in this case C, which can handle 1.6 amp, and repeated the test with another battery. Sure enough, the overshots were gone. They were caused by a bug in my auto range algorithm. You see, when the current suddenly jumps above what the momentary range can handle, my auto range algorithm detects that the shunt voltage is too high, selects the best resolution range for the new situation, and sends a range change command to the INA219 chip. The bug is that the algorithm then passed the originally measured value on for display and recording instead of waiting for the INA219 to report a new set of measurements after the range change. This is now fixed, but if you are trying to get the fastest sampling rate, it is still best to use manual range and set it to the highest range D. On the penalty of a slight reduction in resolution and increased noise, this avoids the overhead of the auto range algorithm itself, the I2C bus traffic to set the new range, and the delay caused by the chip switching to the new range, and the necessary rereading of the chip's registers after the range change. Speaking of the sample rate, you will have noticed that the plots all contain these sharp voltage and current needle pulses. The only way to see if these are real or another bug in my program is to use an oscilloscope, which is what I did next. Here you see the voltage across the shunt resistor, in other words the current. The scroll time is set to 500 milliseconds. The charger is in the green blinking or pre-charging mode. It is clear that needle pulses are real. Here's one of them enlarged. The pulse is 5.6 milliseconds wide. You can also see there appears to be a pattern. 2 pulses of about 2 seconds length followed by a slightly longer gap, and overlaid a continuous heartbeat of 5 millisecond needle pulses roughly 1.5 seconds apart. By chance, I just managed to catch the change between the green blinking pre-charge phase to solid red charge phase on the oscilloscope. The scroll speed was set to 2 seconds per division. Increasing the scroll speed to half a second shows the sequence of about 1 second charge pulses with very small pauses in between and still the same regular heartbeat needle pulses. Zooming in to get more details, the gap between the large charge pulses is about 30 milliseconds and the needle pulses are still 5 milliseconds long. Here are the same plots from the INA219 with resolution pushed to its maximum. The pre-charge pattern of 2 pulses with a longer gap in between is clearly visible, as are the charge pulses. The heartbeat needle pulses are sometimes there and sometimes missing. This is because the sampling is still too slow to ensure that they are all captured. Even for these plots, to speed sampling up, the INA219 average had to be set to 1, which means no average at all, and the data is noticeably more noisy than before. The good news is, however, that the pulses visible in the Powermon recording are indeed real. Let's test a few more batteries. Here is a Uniros 2000 mAh cell. By the way, the light in the first 5 seconds shows the charge status, so red for less than 25%, green for more than 80% and orange for anything in between. After a minute or so in the refresh phase, the charger makes one attempt at pre-charging and then flags up the dreaded blinking arrow light for which the Energy8 is famous. An Energizer 1850 mAh cell. The arrow light comes up even more quickly. And the same happened to a second Uniros cell. Testing a second Energizer cell that had a bit more charge left in it. The charger had no problem with it and goes right to full charge mode and stays there. A pretty empty Duracell battery is going through the pre-charge and then into the charge state without any problem. And just to round things off, the attempt to charge a non-rechargeable alkaline cell. Let's have a closer look at the recordings. The one thing all the failed charge attempts have in common, and they are all marked here with red crosses, is that the cell voltage during the charge pulse is a lot higher than normal. The first Uniros rises to almost 1.7 volts, while the first Energizer drops at close to 1.8 volts, and the second Uniros also sits at around 1.7 volts. The non-rechargeable AA produces a top voltage of 1.8 volts during the charge attempt. Comparing this to the two good cases, the second Energizer, which was almost full, rises to a little above 1.5 volts, and the empty Duracell just to 1.5 volts. It is clear that the charger looks at the voltage of the cell during the charge pulse, and if that rises over a threshold, then the error indicator lights up. This mechanism is primarily to detect non-rechargeable batteries, but as we have seen, it catches some rechargeables as well. So what makes the cell voltage go so high? We know nickel metal hydride cells have a nominal voltage of 1.2 volts, and the end of charge voltage is between 1.4 and 1.6. The answer is a raised internal resistance. You see, the cell voltage has actually not increased at all. If you look at the case of the first Uniros battery, the cell voltage is around 1.15 volts, so quite normal for an almost empty cell. It only shoots up to almost 1.7 volts while the charge pulse is applied. This means the extra voltage actually comes from the charger, and the high internal resistance of the cell together with the charge current causes the excessive voltage. We can even get a rough estimate of the internal resistance from this graph. For the first Uniros, for example, the voltage difference between before and during the charge pulse is, say, 1.7 volts here and 1.15 down here, something like 550 millivolts. Divide that by the charge current of about 400 milliamps and we have 1.37 ohms, which is a huge value for a battery. This is of course only a ballpark figure from squinting at the plots. A more precise measurement of battery internal resistance can be done using this method. It gives the DC resistance, which is an important caveat because the battery also has a frequency-dependent AC resistance, and with the Ansmann charger and its 5 millisecond pulses, this may actually be the one that counts. However, that one is hard to measure, so let's try the DC resistance instead, which is a relatively simple procedure of 3 steps. The only important part to remember is that step 2 and 3 must be done very fast because connecting the load starts discharging the battery, which will skew the results. So note the value in step 3 as soon as possible after connecting the load, definitely within a few seconds. The value of the load resistor determines the sensitivity of the measurement and ideally is in the same region as the suspected internal resistance, but on the other hand should not overload the battery. 4 ohms for a 1.2 volt cell would be 300 milliamps, which looks like a good compromise. It turns out that some suspect batteries like the Uniros are quite tricky to measure because their voltage under load isn't at all stable. Energizer 1, Uniros 2, Energizer 2, Duracell. Here are the results of the measurements. The 2 Uniros cells definitely stick out with their very large internal resistance. The Energizer 1, which was also rejected, is not quite as bad, but 3 times the resistance of the other good Energizer. It appears that the charger is quite sensitive to batteries with high internal resistance. Does this mean these cells need to be going into the recycle bin for dead batteries? To find out, I took the first Uniros here and charged it for 10 hours in a dump charger at 150 milliamps and then run a discharge cycle. Using Powermon to discharge the Uniros cell into a resistor of 10 ohm. After 10 hours and 25 minutes, we see that the cell still had a capacity of about 1250 milliamp hours. This is of course much less than the original 2000 milliamp hours, but still very usable. Of course there could be other things wrong with it as well, such as a high self-discharge, but in general I would hesitate putting this cell into the recycling bin yet. To wrap things up, here's a chart explaining what I think happens in each of the phases of the Ansmann Energy8 charger when charging nickel metal hydride cells. It's going to be the same for C and D cells, and the only difference for AAA cells is a slightly lower charge current. Charging 9-volt batteries follows the same principle with even lower current pulses. The key characteristics are: refreshing is the only time the charger actually discharges a cell. We have an almost constant discharge interrupted by short pulses of charge current, but overall it's a net discharge. This phase is sometimes skipped by the charger. During pre-charging, we have a pattern of 2-second charge pulses with either 2 or 4 seconds gap. Charging uses an almost constant current that is briefly interrupted by 30 millisecond gaps every 1 second, and the ready state keeps charging with quite a high current pulses of 2-second durations followed by 8-second gaps. So this is far from what you normally call a trickle charge. While this is all quite straightforward, I'm wondering about the purpose of those short needle pulses that are overlaid above all of this. Could they be used to measure the status of the cell more accurately than monitoring simply the voltage while charging? The pulses are so short they could definitely be looking at the cell's AC properties. It isn't all that clear what the charger uses to move from one phase to the next. It could be the cell voltage, but even without the complication of the needle pulses, there are two to consider, namely the voltage while the charge is being applied and the one in the pauses between charge current. Since the dense current plot lines normally obscure the voltage curves in my plot program, I modified it for this graph by artificially setting the current to 0 for all plot points. This trick allows me to show you the full voltage curve of a charge from empty to full without having the obstruction of the current plot, which collapses to a horizontal line, which you see here. As you can see, we have a voltage band here, caused by the cell responses to the charge pulse. You can clearly see the phases of the charger, and I marked them with vertical lines. It is possible that the charger uses either the upper or the lower voltage curve to determine when it's time to switch, because they have pretty much the same shape. At least for the switch from charge to ready, I don't think the criteria is simply max voltage, because as you can see, both the lower and upper voltage curves appear to be horizontal for quite some time. I therefore suspect that the charger is detecting that the voltage hasn't changed anymore after some time and uses that as an indicator that the cell is full. I hope you found this useful, and while the Ansmann Energy8 Plus has not revealed all of its secrets, I for one have now a much better understanding of what's going on and why the dreaded error light comes on. You could say that if this charger is successfully charging your battery, it's definitely a good and reliable battery. If it doesn't like it, the battery is certainly damaged in some way. It may be totally dead or just lost half of its capacity and increased its resistance, but still be able to power some uncritical applications, but don't plan using it on your GPS away from civilization. I for one like the Ansmann Energy8 Plus charger much better after this investigation, but I also won't throw away my dump chargers for those special cases. For those interested in Powermon, I updated my Github page with the latest version and fixes. Links as always in the description below. Thanks for watching.